Okay, so good morning everyone, and welcome to the fourth day of the seventh symposium, Amazonian Symposium on Physics. We'll start with the morning session, and today we have the pleasure to welcome Rafael Bernar from UFPA, and Rafael is going to be telling us about quantum states and superradiance in charged black hole spacetimes. Rafael, the stage is yours.
Thank you, Professor Carlos. So this seminar is, as Carlos said, is about quantum states and superradiance in charged black hole spacetime. So basically, Rice and Boston spacetime. And this is basically a couple of works I have done with Professor Crispino, Professor Mustang from University of Sheffield, and one of her students, Isaac Malakuma. So let's begin here with a little introduction. So some things that we know about black holes are that they are very interesting, but they are also very weird. And I don't know if this is a good thing or a bad thing. I think it's a good thing, but and the thing is that they also they actually do seem to exist in nature, and they can tell us a lot of things about seemingly unrelated topics like thermodynamics, particle physics, string theory, and quantum field theory, and so on and so on. And this thing that happens with black holes, that they are weird in the classical regime, and they are also weird when you introduce the quantum realm around. And of course, we know that if you use QFT in curved spacetimes, you can learn a lot about what black holes are doing in this realm. So the fact that they radiate, so Hawking radiation. And another interesting thing that also happened with, basically together with the black hole radiation, is that the Umbro effect. So we will talk a little bit more about that. And one thing that you do around these subjects is you study the Schwarzschild solution, right? So and there you can, as Professor Atsushi told us on Monday, you can define a lot of quantum states there and study their properties. And the thing, one question that we want to answer in my talk is, what can we say about quantum states in other solutions of black holes space-time, right? And so I will try to be very quick around this part here, and especially because Professor Atsushi did the work for me on Monday, so thank you, Atsushi. But so I will try in one slide to summarize what you can do when you quantize a field on a curved space-time. So I'm using the scalar field. You expand the scalar field in this form here. So in terms of solution, classical solutions, so this phi plus, phi minus are classical solutions of this equations of motion. And the coefficients are actually quantum operators in a Hilbert space. And you have a collection of sets here. So there are what we basically can call quantum numbers. So it can be the frequency, it can be the L and M angular numbers, and so this can be a discrete or a continuum set, right? And as we know, one of those is what we call the particle creation operator, and the other is a particle annihilation operator. And they have to satisfy a commutation relation that's basically given by this form here. And when you define these operators, you have a vacuum state that you can define as the one that is annihilated by all the annihilation operators. And one thing that's implicit here is the choice of the classical solutions you are going to use here will basically imply that you have already chosen a vacuum state in this definition here. So basically I want us to remember that if you choose a certain set of solutions of the classical equations of motion, you are basically choosing a vacuum state in this. So vacuum in this definition is defined by this thing here. And so what in the language of a quantum field theories in curved spacetime, you say that the choice of a classical solution is basically you are picking a notion of what you call positive frequency in this spacetime. Basically you want to write in simple terms, you want to write a quantum field as something that depends on e to the frequency used in this construction here. So the notion of a positive frequency mode will influence the choice of a vacuum. And so one thing that we can try to understand a little bit more about is studying quantum field theory in a curved spacetime that's not curved, so on a flat spacetime. And there is one of the things that Andrew did in his very famous work is you study flat space-time, but you use a notion of time that is natural to uniformly accelerated observers in this space-time. So these accelerated observers, they have a hyperbolic motion, and you can study involves 2D involves space-time in this coordinate. And when you write the modes associated with this time here, is the time associated to accelerator of observers. As I said, with this definition, you are picking a certain vacuum state, and the surprise here is that this vacuum state is not what you usually call the Minkowski vacuum state. So it's a surprise that this kind of modes here are actually a mix between positive and negative frequency Minkowski modes. And because of that, the Minkowski vacuum is instead of being empty according to a uniformly accelerated observer, it actually full of what we call angular particles. And so the Minkowski vacuum is a thermal bath of irregular particles for a uniformly accelerated observer. And so there are a lot of things to say about the Andrew effect, and to the interested people in the audience, I always direct them to this review by Crispino and Natsushi and George Matzes that it's actually very, very interesting. And it's basically the one reference in which you can get almost all information about the Andrew effect that you want. Yeah, so this, as I said, this thermal bath is actually, it has a temperature, so the Minkowski vacuum is hot. Sorry?
2008.
2008, yes, okay, sorry. Yeah. So, as I said, the notion of particles is observable dependent instead of only a thing that you can define as independent of the observer. So let's talk about similar effect that happens in quantum field during curved space-time is the Hawking radiation, and it's, I mean, I will not present here rigorous derivation of the Hawking radiation, but one way of trying to understand it is basically if you write down the Schwarzschild metric near the horizon, you get a space metric that is very similar to the regular metric in flat space-time. And so you can define an acceleration felt by a static observer, and you can use the equivalence principle to basically tell that an observer that's freely falling into the horizon, it must see a Minkowski-like state. And so, because of that, a static observer will see a thermal radiation of angular-like particles instead. And this radiation will propagate to infinity, and you have to consider the redshift, but in the end you get a temperature that's basically the surface gravity over 2 pi, so it's this number here. And so for experimental evidence about that, well, we don't actually have any, I think, but you can, because for instance, a normal size black hole, the temperature should be around 10 to the minus 8 Kelvin, but you have some studies around analog models, so you can try to see the Hawking radiation surface waves or the phonons in the Bose-Einstein condensate. But I say that this is actually aligned in Christine and Natsushi work review about the only effect is that basically you can basically tell that Hawking radiation and the only effect, they don't actually need much more than the fact that quantum field theory exists, quantum fields exist in nature. And so if you believe in quantum field theory, and that the fact that they work is basically should be enough to believe that Hawking radiation, the only effect, exists. So one crucial condition, I will go very quick around that, but so one crucial condition for the Hawking radiation effect is you have to assume that there is a Minkowski-like state in your theory, and it is related to one thing that we call the Hadamard condition, and basically you can link that to the structure of the 2-point function of your field, and it has a singular structure that if you want your field to be well behaved in the sense that it's similar to the Minkowski-like state, it has to obey, it has to have a singular structure that is very similar to this one. And with that, you can try to normalize the divergence that happen in the express energy tensor of a field. So in flat space-time, basically what you do is, if you take the stress energy tensor of quantum field, is you can just remove the vacuum contributions by normal ordering. But in curved space-times, you have to enforce the Hadamard condition first to basically realize that the field you have in the state that you have is basically similar to Minkowski. And then, of course, you can then renormalize it. And normal ordering, as Sushi said, is not an option there, but the first step is you need to enforce Hadamard condition. So let's just talk about a little bit about states in Schwarzschild space-time. So this is the Penrose diagram of Schwarzschild space-time. And one way to study that is you have to use a basis of solutions of the classical fields, classical equations of motion, and those are the inmodes, right? So the inmodes come from the past infinity, and they scatter. A part enters the horizon, and a part scatters back to infinity. And we also have in a black hole spacetime, we have the up modes, that they come from the past horizon, scatter of the geometry. A part enters the horizon again, and a part goes to infinity. So I want us to pay attention to the up modes because they are the ones that the interesting thing happens here in those modes I see. So in the Schwarzschild case, you can define what we call polar state, and this is basically the naive quantum state that you can define. Is you define modes that are positive frequency with respect to the usual Schwarzschild time, and in this case you have no fluxes in the infinity, in the asymptotic infinity, but you have the stress energy tensor of this field will be the expectation value of the stress energy tensor of this quantum field will be divergent. I think Atsushi showed us basically should be version of this result here, and you can see that the divergence is basically the absence from the vacuum of the thermal radiation distribution here. So a thermal radiation distribution would be this thing without the minus sign here. So we can also define the unroot state in this case. So in the unroot state, you end up with thermal flux at future zero infinity, which is called irradiation. And you have a divergent at the past horizon, but of course in this case it doesn't matter because you expect the unroot state to describe the quantum state of a black hole that comes from gravitational collapse. Right? And the stress energy tensor in this case is regular outside and inside the black hole. And the way that you define the unroot state is, as I said, so the up modes are the ones that are important here. The in modes you can define using the notion of time, that the Schwarzschild time, but the up modes you define them as positive frequency with respect to the Kruskal capital U coordinate instead. And you can also define what you call the Hartle-Hawking state, and in this case you have fluxes at both infinities, and this describes a black hole that's in thermal equilibrium with a thermal bed, and so you have an incoming flux and an outgoing flux, and those are equal. They have to be equal to thermal equilibrium. In this case, it's regular everywhere, so it represents an internal black hole in thermal equilibrium for each bed. And in this case, the way that you do that is you define modes that are positive frequency with respect to the Kruskal time for both in and out modes. Let's go very quickly about first spacetime in this. So this is the parametric, and you can study quantum states in the parametric as well. With a neutral scalar field in this case. And one very important result is that in the first state, you cannot define a Hartle-Hawking state in Earth spacetime. So So interestingly, you would expect that at first you would expect that there is nothing in the first baseline that prohibits hard Hawking like state at first. But then you realize that, of course, the space-time is rotating, right? And in this case, one way of understanding the K-wall result, so this theorem that there is no hard Hawking state is a very important theorem by Bernar and Hall. And so one way to understand this K-wall theorem is to try to see a very simple picture of, if you look at a black hole and it's emitting radiation, and you want the emitted radiation to be in equilibrium with the black hole, you realize that the thermal mass must rotate rigidly with the black hole. And in this case, there is a speed of light surface. So if the thermal mass would rotate rigidly with the black hole, you would have particles that would be rotating with speed greater than the speed of light. So this is one way to understand the K-wall theorem, a very simple and probably not. So if you try to read the K-wall theorem, it's much more complicated than that. But one way to try to understand that is using this simple picture here. So the idea of the work is what you can say about the scalar field quantum states for Heisenberg space-time, because you can try to circumvent things that happen in the K-wall theorem using a Sharp scalar field in Heisenberg space-time, and of course you can study the Sharp scalar field in this case. So the model that we use here is a massless charge scalar field in a charged black hole space-time, and so the equation is very similar to the one for the neutral field in Kerr space-time. But of course, you get spherical symmetry, so it's much more simple. But the thing that's very similar is that if you look at the potential near the horizon, you have this term here, so omega minus the charge of the field times the charge of the black hole over the horizon. So this term here is, we know that this leads to superradiance, and so same thing happens in Kerr space-time, of course. And so every mode with omega less than this quantity here is the charge of the scalar field times the potential of the electric field coming from the black hole. You get superradiance. So the rotation case in Kerr space-time is decent, and the condition for superradiance in rising Northern there. So in the case of rising Northern, you define this as charged superradiance, because in the Kerr space-time, the black hole loses energy in the angular momentum, and in the case of a charged black hole, the black hole loses energy and charge. So you can study that as a quantum thing, right? So in the quantum version, it leads to spontaneous emission. So the black hole loses charge. So it tends to lose charge by spontaneous emission. And for the rotation case, it's going to start against the radiation. So let's just be very quick around the modes in the rising Northern is basically the same as Schwarzschild. And so you have in and out modes, and you have the positive frequency conditions that omega has to be greater than 0. But for the utmost, it was the frequency conditions that omega tilde has to be greater than 0. So you may recall that the omega is omega tilde is omega minus something, right? Minus something that's positive. And so this leads to a very interesting thing, is that when you try to define the vacuum states in those, for instance, what we call the fast polar state. So let's say you want to define a quantum state in rising noise for the charge scalar field, that you will define it the same way that you define the polar state before. So same thing. In this case, recall that for the Schwarzschild case, we don't have fluxes at infinity, but in the Rice and Morrison case, you have a flux at infinity for the polar state, and it's not all in radiation here. So this radiation is a flux of superradiant particles. So this basically is modeling the fact that the black hole is emitting charge as time goes on. And of course, we call it fast polar state because there is no flux at fast infinity. So one of the ideas that we had was, can we define a true polar-like state in Rice-Morrison? So one that has no fluxes at no, and so there are a lot of technical things that we have to do this, but one way that we can try to understand this equation here, that if you want to compute an observable in this supposed polar like state in Rn, you have to compute something like that. So this O here is the contribution from the in-modes to the observable. And this O up here is the contribution from the up-modes to the observable. And one way in this equation here, you can see that basically you have the contributions from all the modes here, but then you subtract the contribution from the up modes from this thing here. And this is, you can do that, and it actually makes sense with the fact that it is an intermediate state, so you don't have fluxes. But when you try to compute some observables, you will see that there has a lot of problems. So the way that you have to understand this clause here is we call that in Atsushi's seminar, the capital U is 0 at the horizon. So capital U at future horizon is U equals 0, right? So to see how a quantity diverges in the future no horizon, you have somewhat compute a finite quantity there, and you try to use the powers of F here to control this divergence. So one important thing that happens when you go near the horizon through a fixed capital V direction is that the U variable goes to 0 as 1 power of F. So U approaches 0 as F of R. Right? So this is one important thing to remember. And so you try to balance this divergence here with a power of F here. So, for instance, this graph here is what will tell us that this current is not well behaved because you have to balance the divergence with 2 powers of F instead of only 1 power. So the current is not well behaved in the future, no horizon. the same thing happens for the other component of, this is the charge, the current density for the charge scale. So both, so the currents are not very basic. So same things happens. Energy of a moment like state. This is the charge. So current density. Another result that you can have is try to define Hartle-Hawking like state. And it's given by that. So this potential is hyperbolic. Potential is basically the thermal factor, right? And you can by that. So this is the thermal factor here. In these cases, you know it's in the liquid state, so this time reversible area. And you can compute things like that. So one thing that is not here in the plot, but those quantities are actually differences in expectation value from this tentative state that we have, this Hartle-Hawking like state, and a known state like the Omni state, right? And this plot here is a sanity check that you can do to see if things are working, because we know that this quantity is conserved in those quantum states, so this quantity has to be a constant as a function of R from the conservation equations. So to see if the numerics are working good, it's better that those things are as straight as possible, right? So if you zoom in, it's actually those things are actually not straight because you have an oscillation from the fact that your numerics are not accurate, 100% accurate. But if you zoom out, you can see that it's basically a straight line. And of course, this represents the fact that so if you compute these quantities for the unloop-like state that you have in Rn, you will see that it's the same plot, actually. So basically, this tells us that the Hartle-Hawking state doesn't emit anything, because you have a balance of fluxes so all the information about the fluxes here is coming from the unloop-like state. And so when we looked at those graphs, it was actually very promising for us, because if you look here, you have one over U, 1 over capital U here, and you have, it's better for your quantity to be finite if you multiply it by 1 power of that. So it's actually, so this result here is good for us. The same thing for the JV component. So the JV component, you don't have to multiply it by any function of f, because only the U component, only the capital U coordinate is 0 at the future horizon. So this V here is basically just a finite, it's a parameter that you vary if you want to look at the future horizon. So basically, U equals 0 is the future horizon, and V controls the point of the future horizon that you are probing, right? So this is also good for us. But so at this point we were hopeful that we would actually define a Hartle-Hawking like state in Rn, and basically we were going against the K-wall theorem. But of course, things are not that good in light. So actually, when you compute the stress energy tensor, you have divergence near the future horizon because you have to combat two powers of F here, and the quantity is finite that just one power of F to multiply by. So the stress energy tensor is divergent at the horizon, and a similar result holds for the liberal scalar field space. So with that, of course, we had to look at other states in the cognitive papers, but those are actually a summary of our results because other states had other pathologies and we were hopeful that hydrovolcanic light state would exist in this case, but it seems it's not, wasn't to be so. Some final remarks, right? So we actually redefined the polar light state because it is as empty as possible at no infinity, but we saw that it is badly divergent at the horizons. But this is, well, the polar state which Washington also has those properties. So one question is, are there other pathologies? Because since we constructed this polar light state in a kind of, we took from our pocket some from first principles. And so it might have other pathologies like negative normal states. Of course, one other thing is that we didn't compute any renormalized quantities. So we basically computed difference from expectation value. Since we know how one of those quantities behave, you can infer the properties of the other quantity by those differences. Right? And it appears, of course, that the hydrovolcanic state is not well behaved, and you can try to do that for instance, fermionic fields, and of course try to do other ways to circumvent the K-wall field. So that's all. Thank you for that.
Thank you, Rafael, and also for giving the time. I believe we have time for a few questions, and I ask the audience if there are questions. Well, it would be better if you've come here, so please come here.
Yeah, thank you for that. So there are no state regular on both horizons.
On both horizons, I don't think there are no.
There are no.
Yeah.
Oh, I see. Okay.
Yeah. So basically, what you were trying to do is the hydrovolcanic state.
Yeah.
We were hopeful that it was regular at both horizons. Because we talked with Bernar K, and it seems that if you look at the K-wall theorem, it's not really that clear if it works for charge and scalar fields or not, because there are some interesting things that you can try to circumvent the hypothesis from the theorem. So we were hopeful that Bernar K would just tell us the answer, but it doesn't actually know.
So I don't think so. So there are no unrule like say either.
Yeah. So basically, the derivation for the K-wall theorem that works for Earth space-time should work for Rice-Norton space-time. since the theorem is very hard to follow in the right, I don't think anyone has done that. So basically the expectations is worse, but nobody has done it.
All right, thank you.
Thank you very much, Atsushi. Are there any further questions from the audience? I see no questions. Maybe I can ask you a question, which is kind of unrelated, but nonetheless I'll ask. Because we've talked a lot about quantum field theory on Earth spacetimes, and I guess especially in these context of black holes, accelerated observers, there's been a few other applications that are interesting. And one of them that I thought was very interesting was Hawking's attempt to show if closed time-like curves are actually disallowed by the laws of physics. So he has this very interesting paper called Chronology Protection Rejection, in which he uses a toy model. It's kind of flat space-time, some identifications, such that you can form a closed null curve and then closed time-like curves. And his argument is that the renormalized energy momentum tensor diverges this closed null curve. And well, this was interesting, but it was not generic. So my question to you, and of course, if you say you haven't thought about it, it's perfectly fine, but is one at the think about this and about the possible generality of this sort of argument in ruling out space times with closed time-like curves and closed null curves.
It's very interesting, but also I haven't thought about it.
Okay.
Yeah, when I read the paper, the argument is basically since it diverges, so there are probably, if you try to compute some approximation of that and that creating from the geometry, so the null curve will open instead. So you only have the time-like closed curve if you don't consider that creation. But since we don't actually know how to do these computations and do a lot of generic situations, basically nobody knows this.
Yeah, I think that the setup it chose was very simple because again it was flat space-time where we know the modes with some identification, so it selects a part of the spectrum. And then the argument was what you said, that the back reaction would either promote a singularity, which is unphysical, or kind of counteract the effect that's forming the closed time-like curve or closed null curve. And so it would be a sort of inertia of the space-time towards causality violations. But again, it's a very simple toy model. And but of course, Hawking ends the paper saying, this well, is why we haven't been visited by hordes of tourists from the future. So that's a famous punchline. Anyway, so I think that would be interesting to discuss further. So thank you very much, Rafael. Thank you. Let's thank the speaker again.